All right, just a quick video here to see how we can use those standing wave conditions to solve some simple problems. So we're going to say the speed of sound on a string is 380 meters per second. In a previous video, I discussed how you can calculate the speed of sound on strings, so we're just giving it to you here. The length of a string has 50 centimeters and it's fixed at both ends. Find the fundamental frequency, first and second overtones. So we're interested in the n equals 1, 2, and 3 standing waves that exist on this string. Because it's a string that's fixed on either end, we can use the formula L equals n lambda over 2. And we're going to use the values n equals 1, n equals 2, and n equals 3 here. I'm going to go all the way through with n equals 1, and then I'll show you n equals 2 and 3 quickly as well. So if the length is 50 centimeters, don't forget to go to meters, lambda over 2, then the first possible wavelength works out to be 1.0 meters. If we know the speed of sound on that string, then we can use the universal wave equation to come up with the frequency. And the frequency in this case will work out to be 380 hertz. So if we tighten the string down to the point where its speed goes up to 380 meters per second, it's a length of 50 centimeters. If I pluck that string, the main frequency that I'm going to hear produced by that string is 380 hertz. But what other frequencies are produced? Well, let's go to the n equals 2. In this case, L ends up equaling lambda directly, and so my lambda is equal to 0.5 meters or 50 centimeters. Again, using my universal wave equation, I can see that I'm going to end up with a frequency of 760 hertz. So that's the fundamental frequency. That's the first overtone. That also would represent an octave musically. All right, n equals 3. 3 lambda over 2. So my length is 0.5. 3 lambda over 2. So I multiply by 2, divide by 3. And I'm going to get 1.0 divided by 3. 0.3333. I could continue, goes on. And now using my universal wave equation, V equals F lambda, 380 meters per second, frequency of 0.333 meter wavelength. And I get 1,140 hertz. So this is the fundamental frequency, the first overtone, and the second overtone that would be produced by that string. All three of those frequencies would be present. The distribution of them would make up the quality of the note, but most of them would be at the 380 hertz range.